In this tutorial, we will be talking about variational autoencoders. But before that, we have to talk about traditional autoencoders. So the way traditional autoencoders work is, imagine you had an input image, and in the case of MNIST, which we will be showcasing later, that will be a 28 by 28 pixel image. And for simplicity, let's flatten this into a vector which has a dimensionality of 784. So in autoencoders, this vector would go into the so-called encoder block, and afterwards we will have another vector which is called the latent vector, and this vector is much smaller than our original vector, which had a dimensionality of 784, and this latent vector could have, for example, 128 dimensions. Afterwards, this latent vector goes through the decoder block, and the decoder block outputs another vector which has the same shape as the input image, or input vector in this case, which is 784. And if we reshape this into 28 by 28, then if the autoencoder was trained correctly, this will output the original image back to us. So why did we do any of this? Well, the reason is that after we trained this autoencoder, we have this latent vector. And the latent vector contains just enough information to reconstruct the original image while being significantly smaller than the original image. For example, you could have a neural network which classifies some images or something, and instead of passing the entire original input image, which can be pretty big, you would first pass it through this encoder and get a much smaller representation and then use that instead. In theory, this much smaller representation should still be enough because we showcased here with the decoder that it was possible to reconstruct the original image just from this latent vector. So before we continue with variational autoencoders, let's quickly implement this traditional autoencoder on the MNIST dataset. So here I already went ahead and created the autoencoder, and most of the stuff should already be familiar to you because we covered this in a different video. But the dataset that we're using is the MNIST dataset, and the autoencoder here consists of the two parts that I mentioned earlier, which is the encoder and the decoder. In our case, that's both a sequential layer, and those sequential layers, they consist of a linear layer followed by an activation function, which is ReLU in this case, followed by another linear layer. And if you have a look at the dimensions here, you can see that dim, which is the initial input dimension, goes to a hidden dimension, which is usually smaller than the original dimension. And then you have another layer that goes from this hidden dimension to the latent space. And then for the decoder, it's the other way around. So you start at the latent space, then go over to the hidden dimension, and then finally from the hidden dimension to the original input dimension. And the way you use this autoencoder is you just simply pass in your image or whatever your input is. And then that first goes through the encoder, which gives you the latent vector. And then you run it through the decoder and get the reconstructed output. Here in the loss function, we simply compute the mean squared error between our reconstructed output and the original image. And this step function is normal boilerplate JAX code. And then over here, we actually train the autoencoder. And finally, after the model is trained, we try to reconstruct the original image. So if I run the training, then you can see after 20 epochs that our autoencoder has become pretty good at reconstructing the original image. And mind you, this is coming from the latent vector. So we compressed this original image into a smaller representation and still managed to reconstruct the original image. Now this is only after 20 epochs, and if you trained this for longer, you would get a closer representation of the original image. So now that we have covered autoencoders, one reasonable thing you might be asking is how can we use this latent space for anything useful? And instead of focusing on numbers, we'll simplify this into geometric shapes. So for example, you could have an image of a circle, and then you would put that through your encoder, and that maps your original image, which is the circle, into this latent space. And we can just say that that point corresponds to somewhere over here. And now if you had another image, let's say this time it's an image of a square and then you put this through the encoder, then the encoder maps it to perhaps this point. And you might be wondering, wait a minute, if I know that this point over here, that's a circle for sure, and this point over here, that is a square for sure, then if I pick the point in between these two reference points, then I should get some image which is in between a circle and a square. So perhaps something like an oval or something. So what you would do is you would put your circle through this encoder, get some vector, then put this square into the encoder, get another vector, compute the point in the middle, and then put that through the decoder, and then hope that you would get some kind of oval back. And then you would have some kind of infinite oval generating pipeline. But unfortunately, this just simply does not work. This latent space from the autoencoder is incredibly unorganized. So much so that if you move in any direction, then that move doesn't really correspond to anything. So you couldn't actually move in the direction of a square and then hope to get something in between because the latent space is just way too unorganized for that. So even if you take this reference point for the circle and just slightly move in any direction just for a small step, then what you would get as a return wouldn't even look like a circle. And if you move too close to this point, well, then you would just get the original image back. And this is a problem because, well, ideally we would want to generate these oval shapes by just simply moving in between these two shapes. But we can't do that with the autoencoder, so what do? Well, the solution is to organize this latent space. And that is exactly where variational autoencoders come into play. What they do is essentially organizing this latent space in such a way that if you move in some direction, similar to what we did here, that you would actually get an image back which makes sense. Okay, so in variational autoencoders, we have two spaces. One of those is P of X and another one is P of Z. And this space right here, that's our data distribution. And we don't really have access to this data distribution. We just have a few samples. But other than that, we don't really know this. And this right here is the latent space, and we also don't have access to this. It's a design decision in variational autoencoders to say that this thing right here, the latent space, is normal distributed. We also have two mappings between these two spaces. One of them is kind of like the encoder. So it generates a vector z. So it's the probability to get some vector z given some input x. And then you have the kind of decoder. So it gives you the probability of some vector x given some latent vector z. So these two mappings are normal distributed. And the thing is that we don't really have access to any of these. But if we did, well, our problem would be solved. Though the problem is that at least for the encoder, it's not possible to directly learn the encoder. The decoder is actually pretty straightforward. It's a standard supervised learning problem. You basically just have your reconstructed vector, which I'll call x hat, and then you have your real vector x. What the decoder has to do is to minimize the difference between these. So it's a very straightforward standard machine learning problem. The encoder, on the other hand, is a problem because, well, if we write it out, we have the probability to get vector z given some vector x, which is equal to the probability to get vector x given z times the probability to get z divided by the probability to get x. And furthermore, this is equal to the probability of x given z multiplied with the probability to get z integrated over z, which is the latent space. And this is also the reason why we can't learn this thing directly, because we don't have access to this right here, and we would need that in order to integrate over all possible vectors in this latent space, but we can't do that. So what we do in variational autoencoders, we introduce an approximation Q and say that this Q roughly approximates our real encoder. And if we train everything correctly, then our approximation will indeed, in the end, approximate this distribution right here. So in order to train this thing, or the whole variational autoencoders, we need to derive the loss function. Okay, in order to derive the loss function, we have to first state our goal. And our goal is to maximize the log probability
for P of X. And the reason why this is the case is because we have our data set, which has a bunch of vectors. What is the probability that these samples come from the data distribution? Well, the answer to that is 100% because these are samples from our data distribution, so therefore they must have a probability of 1. By maximizing this probability, we're essentially learning what vectors belong to our data set. So if I had a completely different vector like A, for example, which is not from our data set, well, then the probability would be low because our model has learned which data points do come from our data set. So the first thing we can do is to marginalize out Z. So we can write that this is equal to the log of the integral for Px given Z multiplied with the probability of Z integrated over Z. So just a quick note about what marginalization is. So imagine you had 2 die and those die are skewed such that they have a higher probability to give you a higher number. So if you were to draw the probability matrix, it would look something like this. And this is kind of meant to be like a heat map where areas that are more red, in those we have a higher probability to get this result. And now let's say we're interested in the probability that our X die rolls a 5. So we're interested in this part. And those include events where the X die is 5 and it doesn't really matter what the Z die is because we're only interested in the X die. And those events are where we have 5 and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, and 5 and 6. So if we want to get the probability that X is a 5, then in order to get this, we have to sum up all the probabilities where X is equal to 5 and, well, any event for the Z die, because we have to throw both of them at the same time. So in other words, it's the sum for the probability that X is equal to 5 and given that Z is equal to I times the probability that Z is equal to I. And this process is called marginalization. So in our example, we had an integral sign because we have continuous values. But in this example, since all the outcomes are discrete, we use the summation. The important part is that this process is called marginalization, and therefore we can write it out like this. From here, we can use the multiply by 1 trick to introduce the approximation for our encoder. And we can put these terms together and rearrange in order to get this. And the next trick we have to introduce is perhaps not super obvious, but let's think of an example where we have 2 functions. One of those is f of z is equal to z, and another function, let's call that capital Q of z. And this function gives us the probability to get z. And let's think back to our example with our skewed die and say that this capital Q is kind of the process of rolling the die. And this function right here, that's basically how much the throw is worth. So one question you might have is, what is the expected value for this function? And the expected value for this function is defined as the expectation over Q, that's our random process for our function, and that is equal to the integral of Q for z, and this is the probability to get z, multiplied with our function. Thinking back of our skewed die example, let's say that we have a 10% chance to throw a 1 and a 90% chance to throw a 6 and nothing else. And in this case, the question is, well, what is the expected value for z? So let's say the value for z is equal to z. So if we roll a 1, then the value is simply 1. And similarly, if we throw a 6, the value is 6. We know that the probability to get a 1 is 0.1, and the probability to get a 6 is 0.9. Therefore, the expected value is the probability to throw a 1 multiplied with the value of 1 plus the probability to roll a 6 multiplied with the value of 6. And this is kind of implied that every other throw is 0 So in other words, for example, the probability to throw a 3 is 0, right? And then similarly for everything else. So if we plug in the values, we get 0.1 multiplied with 1 plus 0.9 multiplied with 6, which comes out as 5.5. So in other words, if you were in a casino and this is the game, and to enter this game you would have to pay $5 and then you throw the die and then you get back whatever roll you get. Well, in that case, you would obviously do that because you're expected to get 5.5 back, but it only costs you $5 to play. So that would mean that you're making profit. So the last step in our derivation as of now was this. And this is kind of like the same setting we had in this example over here, where this part would be like the capital Q for this example. So that would be like the capital Q part, and this is kind of like the value part, so F. This means we can write this part over here as an expectation. So we can say that this is equal to the log of the expected value for our encoder. The next trick we have to use is called the Jensen inequality. And this is true if the function is a concave function. And because the log is in fact a concave function, the Jensen inequality holds. So in other words, we have this log probability, which now is greater or equal to this expected value. So it basically just moved the log inside and replaced the equal sign with this greater or equal sign. And this is now pretty neat because if we somehow are able to increase this, then that would also increase this log probability. So from here we can now split this part back to its original form. And from here we can use the laws of logs, I guess that's how you would call it. Those state that the log of a product is equal to the sum of its logs. So in that case, that would be log of x plus log of y. And similarly, if we have a division here, then that is equal to log of x minus log of y. So if we use both of these laws, we can write the expectation as the following. The next trick we have to use is called the linearity of expectations. Basically, if you have a sum in your expectation, then you can split that sum up into two expectations. So this is very close to our final loss function, and we have these two parts. The left part here, where I said in the beginning that the probability to get some x given some z, this is our decoder. So this part kind of trains our decoder, where this part over here kind of trains our encoder. And what's neat about this is that if we start with the decoder, this part right here will simplify to the mean squared error. And the reason why this log probability simplifies to the mean squared error is that if you write everything out, you get the following. And remember that this decoder is a normal distribution. And actually what I didn't mention before, because a normal distribution requires both mu and sigma, the decoder in practice only uses mu and sets sigma to some constant. But if we write this out, then we get this formula where x hat is the reconstructed value from this latent vector z. So if we slap a log in front, then what happens is that this cancels out the expectation. So what we're left with is log of this part right here, and this only consists of constant values. Remember that I said that sigma is constant while pi and 2 and d, which is the dimension, all these are constants. So this is the log of some constant, I'll call this a, minus this part right here. And again, this is also a constant. So we can abstract this away and put that also into the a. So what we have, and this is again another constant. So what we have is some constant, I'll call this b. So this includes everything that is not dependent on x. So it's b minus this part over here. And everything that is a constant doesn't matter when we train our model. So basically, we can also remove this part right here, and all we're left with is this part where this is the exact definition for the mean squared error. So as I mentioned, this part over here simplifies to the mean squared error. If we have a look at this part, then perhaps the eagle-eyed viewer may notice that this is the definition of the negative KL divergence. So in other words, we can rewrite all this as the following, and the KL divergence measures the difference between two probability distributions, so the encoder and this latent space. And if you remember in the beginning, I said that it's a design decision for variational autoencoders to say that this part is a normal distribution. So what the KL divergence does is to move our encoder to look like a normal distribution. And by the way, this whole thing right here, that is called the elbow, which stands for evidence lower bound. And the goal, well, this part is smaller or equal to the log of this. And our goal is to maximize this part, because if we maximize the elbow, then we're maximizing this log probability. But the problem is our machine learning libraries, they're not designed to maximize anything. In fact, they're designed to minimize some loss. So we have to define our loss, I'll call this capital L, as the negative elbow. So if we minimize the negative elbow, then we're maximizing the real elbow, which in turn maximizes this log probability. This means that we have to invert the signs right here. So we have to say that the loss is equal to this. And as I mentioned a few moments ago, this right here simplifies to the mean squared error. So we can rewrite this like so. And as for the KL divergence, as mentioned in the beginning, because it's a design decision that the latent space is a normal distribution, this whole KL divergence can be rewritten in a closed form like this, where this mu and sigma are the outputs from the encoder. We will see that in just a moment. So yeah, this is the loss function for the variational autoencoder. Okay, so after all that math, I think it's time to write some code. The first thing we'll do is to import everything we need. Then we'll create some loss metrics. This is coming from the common loop utils. Then we'll set the random seeds. And the next part is basically just loading the dataset using TensorFlow datasets. And after that, we have our train and test dataset. And this is just standard boilerplate TensorFlow datasets code. Next up, we'll start with the encoder. So for the encoders, we'll have a sequential layer and also two linear layers, one that outputs the mean and the other one that outputs the log variance. Then we'll create the init method and split the random key, and this is required in order to initialize the layers. We'll start with the sequential layers and simply create two linear layers followed by a ReLU, and then we will initialize the mu layer as well as the log variance layer. And as you can see, we map from this input dimension to the latent dimension. After that, we need the call method, which simply passes the input through our sequential layers and then generates mu and the log variance. And in the end, we will return both of those. That will be required in order to sample using this mean and variance. The next thing we need is the decoder. Again, we have sequential layers, and in our init method, we will first split the keys and then initialize the sequential layer with a bunch of linear layers followed by ReLUs. And the decoder maps from the latent dimension to the output dimension. This output dimension is going to be the same as the input dimension from the encoder. Then we need to define the call method, where we pass the latent vector z through our sequential layer and then return the reconstructed value for x. We put both of those together in the variational autoencoder. So we have the encoder and the decoder. And in our init method, we initialize both of those using the input dimension, the hidden dimension, and the latent dimension for the encoder. And then from the decoder, going from the latent dimension to the input dimension. In the call method, we first get the mean and the variance from the encoder. And utilizing this mean and variance, we need to use, and it's pretty difficult for me to pronounce, but it's called the reparameterize trick. It's not so easy to pronounce. And what it does is basically just takes the mu and the log variance and uses those to sample a vector. And then we get the encodered vector z. And now you might be wondering, why aren't we just sampling using this mean and variance directly? And the reason for that is if we sampled using these directly, then we couldn't compute the gradient of this module. Because what is the gradient of a normal distribution? There is no such thing. Instead, we use this trick, which mathematically comes out to be equivalent to simply sampling directly. But if we do it this way, then our machine learning libraries can compute the gradients. So after using this trick, we get our latent vector z. And from there, we can reconstruct the input using the decoder and then return the reconstructed value for x, as well as the mean and variance from the encoder. And we need those later in our loss function for the KL divergence. So now we can start with the loss function. The loss function gets us input the model as well as the input x and a random key. We split the key and then we first pass the input through our model, which gives us the reconstructed x, mu, and the log variance. From there, we first compute the reconstruction loss. That's, if you remember, the left part of our loss function, which basically is just the mean squared error. And the other half is the KL divergence, and this is the right half of our loss function. And as you can see, we use this log variance as well as the mu in order to compute the KL loss. Then we compute the total loss and return that. We can now initialize the model, and by taking the first sample from our dataset, we can test if our code is correct so far. Afterwards, we define the learning rate as well as the optimizer and optimizer state, and this is JAX specific stuff. Then we create the step function. Again, this is JAX boilerplate. We define the number of epochs, create the metrics as well as a key, and then create our standard machine learning loop. We iterate over the training dataset, we get the images as well as the keys, and then compute the loss as well as the new model and the optimizer state using our step function. Then we update our metrics and print those. These two lines are Equinox specific stuff where we save our model, and this visualize reconstruction as well as visualize samples helper functions are just there to visualize what our model has learned. So we can use those functions in order to get some nice images. So if we run the training now, then after some time when our model is trained and the helper functions are run, we get this nice reconstruction image where we can see the original image as well as what the decoder has generated. And it's pretty good. So as you can see, the reconstructed images are very similar to the original input images. But now the interesting part was the fact that now we can generate new images. So these images, they are not part of the MNIST dataset, and we created those by sampling from the latent space and then passing that through our decoder. And because our latent space is now tidied up, which it wasn't when we had the normal autoencoder, we can now sample new images. And I know that this isn't as impressive as what you can do these days with diffusion models, but at that time, this was actually pretty impressive. So what we managed to do was to structure the latent space in such a way that now we can sample new data points from it. And yeah, that was the variational autoencoder. I really hope you enjoyed this video. Thanks for watching, and I will see you in the next one.